In this lab, an object moving at constant velocity will be observed, and its motion will be used to predict the object's new position. This lab also explores the practical purposes of using a computational model. So, beginning with Newton's second law, the fundamental principle states that when a force is applied to an object, it will move with an acceleration. An acceleration is known to be a change in an object's velocity over a change in time. So we can write these statements algebraically so that we may manipulate the variables in order to find our velocity. Since our object moves with constant velocity in our lab, the object has no acceleration, meaning there is no net force being applied to the object. Therefore, a new position can be found by observing the object's velocity over time and adding that change to our initial position. So, in our lab we have a ball that moves forward with constant velocity. As it changes position, we track its motion on tracker. The ball's position as it moves over time is recorded in this table. So the experimental model that we have created can be compared to a computational model that is created running VPython. When we compare the data that we find in our computational model to the data in our experimental model, we can clearly see both our experimental position and our model position correlate. Therefore, our computational model and the equations that we use to predict the position of the object are accurate in real time. However, some sources of error do exist, because in reality, our net force is not equal to zero, meaning that we do have, or that our velocity varies over time due to gravity, friction, and air resistance on the ball. However, there is a really strong correlation in our model, and some of the error that we see in our graphs may have also been caused by a failure to choose correct points in our tracker model. So, as we can see by our graphs, the ability to predict the new position of the object based off of our equations is very accurate. So, to answer some follow-up questions, if our axes were flipped, or if the ball was moving in the negative x direction, the results would be the same, and our computational model would predict our experimental model very thoroughly. Also, we can easily count how many forces are acting upon the ball. But unless the magnitude of these specific forces are given, we cannot determine the magnitude of these forces using Newton's second law. This concludes our lab and our observation of an object that moves with constant velocity.